All right. Welcome everyone to today's Wolfram Institute live stream. Today we have Lucas Squillante, and he'll be presenting his project from the 2025 Wolfram Summer School, Critical Behavior and Noise Threshold in Consensus-Based Cellular Automata. Lucas, go ahead, take it away.
Thank you very much, Dugan. First of all, I'd like to thank Max, Dugan, and James for this opportunity to be here. And it's a really pleasure for me to present my work that I developed during the Wolfram Summer School. And as Dugan already introduced, this work is about critical behavior and noise threshold in consensus-based cellular automata, a work that I developed during Wolfram Summer School with my mentor being Rafael Caballero. So the schedule or the outline of my presentation. First, I'm going to be make a brief introduction and a brief review regarding phase transitions and critical phenomena. And this is like to set the tone regarding my background. And then I'm going to discuss my project itself regarding the Wolfram Summer School consensus-based mechanism and some results on the project, followed by conclusions and outlook. So first of all, I'd like to introduce the research group that I belong here in Brazil. This is the solid state physics group for the São Paulo State University. The head of the group is Professor Mariano de Souza. He's my postdoc supervisor at the moment. So we have been doing some pretty interesting physics here. We have a solid state physics laboratory, a low temperature physics facility here that can reach of temperatures down to 1.4 up to 300 Kelvin, and can apply magnetic fields up to 12 Teslas. We have been mainly exploring bulk experiments like electric polarization, dielectric constant measurements, a function of temperature and magnetic field. But one of our expertise is carrying out thermal expansion measurements and magnetostriction measurements under this using this low temperatures facility. Um, just to give you a little overview, what we have been experimentally exploring, we have been exploring these so-called molecular conductors of the TMTTF family. TMTTF is this molecule here that is formed by sulfur, carbon, and hydrogen. You can see that on the unit cell, we have two molecules and one so-called counteranion. So this counteranion can be changed, and when you change it, you change the so-called pressure or the chemical pressure in a system. And these systems enable the exploration of strongly correlated electronic phenomena. You can see that their phase diagram is really diverse. So we have like charge ordering phase, a Mott insulating phase, spin pairs phase, antiferromagnetic phase, spin density wave, and even superconductivity. So these systems enable us to investigate very deeply the fundamental aspects of strongly correlated electronic systems.
And is this a
Regarding
crystallographic arrangement? I'm sorry.
Yes. So yes, I mean this is the crystallographic arrangement of the real material. So these materials are grown by electrochemical synthesis, and they are, so to speak, very clean because of the how they are synthesized. So they don't have like defects or inclusions that makes the exploration of strongly correlated phenomena very easy to do, so to speak. So was that your question? Sorry, Dugan.
Yeah, that was.
Okay. Um,
Yeah,
so
also, I was wondering,
sure.
I'm not a physicist, and I assume that some of the listeners aren't as well. So, like, um, what does the phase diagram mean? Like, what do the different colors mean?
Oh, sure. So if you get like a material like copper, you see that if you vary temperature and pressure, it will remain a metal depending on, of course, how high or, you increase temperature or pressure. So it's like a boring phase diagram. If you get like the phase diagram of water, you have like what is known like the liquid, gas, and solid phase, for example. So you know that when you heat up water, you go from the liquid to solid and stuff like that. Here, what I'm showing is that these materials have a diverse uh, amount of phases. So this is the so-called Mott insulator, for example. So this is like an insulating phase. So the system at room temperature is a metal. And then when you decrease temperature, the electronic correlation becomes important enough so that in order to minimize the energy, the electrons have to localize. So this localization, because of the interactions between electrons, is called the Mott insulator. So these are all of the phases that we can reach and can explore experimentally with only this kind of family. So for example, we have like in low temperatures an antiferromagnetic phase, you have a non-magnetic spin pire phase and so on. And even in low temperatures and you apply pressure, you have like a superconducting phase. So this diagram, Willem, what is shown is that if you vary temperature and pressure, you can explore many different phases with a single, so to speak, with single compound. And this is not something that is usual in the literature in terms of physics. So that's why these systems are particularly important and why we explore them experimentally in the lab. Is that okay?
Yeah, that's really interesting. Thank you.
No problem. So we always like to say that the experimental background associated with the lab paves the way for us to explore theoretical works, and that's what I've been doing in terms of phase transition and critical phenomena. So regarding this is the so-called phase diagram temperature versus U over W. So U is the on-site Coulomb repulsion, and W is the bandwidth of the system. So you have on the left of this phase diagram a Fermi liquid or a metal, and then on the right you have a Mott insulator. So this transition between a metal and Mott insulator is governed by a critical point. And then below the critical point, you have a coexistence region where you have like metallic puddles associated with in an insulating matrix. So this is like something that we see in first order phase transitions. We have coexistence region, right? So the idea is that close to this critical point or below the critical point, the coexistence region, you have like a huge entropy accumulation because you have the two competing phases. So insulating and metallic phase are competing with each other, and this increases dramatically the number of configurations. That's why the thermodynamic quantities in the immediate vicinity of the critical point have signatures or thermodynamic signatures, or they are maximized in close to this region. And this is something that is very known in the phase transition and critical phenomena community. And one of the parameters that is particularly important in this sense, the so-called Grunizing parameter, which essentially this is the so-called Grunizing ratio. It's the singular part of the Grunizing parameter, which is only the thermal expansion under constant pressure divided by the specific heat. And then you can rewrite this in terms of the entropy derivatives, in terms of pressure and temperature. So it's like this parameter, it's like it measures how much entropy is being changed in this in particular region you're interested when you vary pressure or temperature. And this is actually, in fact, associated with the so-called caloric effects. We know some of you may know that we have like magnetic refrigeration or stuff like that. And then this parameter, it quantifies how temperature is varied when you vary a parameter. It can be pressure, it can be magnetic field, it can be electric field when you have an adiabatic condition. So this is the parameter that presents a fingerprint close to critical points and phase transitions. And it also quantifies the caloric effects, as I mentioned. So this can be also, this is the so-called classical phase transitions where the critical point is at finite temperatures. And then you have like the so-called quantum critical points that genuinely take place at 0 Kelvin, zero temperature, by varying a specific tuning parameter that I'm going to give you some examples in the next slides. But the idea is that experiments are made in the region close to the critical point. So fluctuations close to the critical point of the entropy are really high because you have the presence of the critical point and the competition between two different phases. And then this is associated with my project that developed during Wolfram Summer School that I will be commenting a little bit later in this presentation. But the idea is that for classical phase transitions and critical points, or even quantum ones, The granizing ratio is the parameter, is the quantity that is particularly sensitive to them. And sometimes in the literature, they're mentioned that they are the smoking gun to probe quantum critical points and phase transitions. And as I mentioned, this tuning parameter can be anything like pressure or the magnetic field or stress or and so on. So just to give you a little glance of what we have been doing, in 2021, after the pandemic started, we did a mini review about how to use magnetic models like the Ising model to to describe the spread of COVID-19. And then we did this by making an analogy to the easy model that an infected people is like an spin up and a healthy person is like spin down. And then you have an interaction between them and then there's a probability of infection. So we have been using like condensed matter physics tools and the Ising model to describe the spread of COVID-19 and how it would be like suppressed in terms of the people in quarantine and so on, just to give a little glance of what we can do in terms of an interdisciplinarity. As I mentioned, quantum critical points are particularly important. In 2020, we did some work about the so-called magnetic field induced quantum critical points. We have two kinds. We have those that the so-called zero magnetic field, zero field quantum critical points that you just have to lower the temperature and then at 0 Kelvin, if this was accessible experimentally, we have the quantum critical point, or you can have a quantum critical point at a finite magnetic field. So they are always at 0 temperature. So what we have shown this in this work together with the co-authorship with Harry Eugene Stanley, for example, is that although you can neglect interactions between magnetic moments in some models, the fact that you always have finite interactions between magnetic moments creates what we call so-called local magnetic field. So this local magnetic field suppresses the fingerprint of the granizing parameter when the so-called zero field quantum critical points. So this work was particularly important in terms of insulating paramagnets, where we made a little contribution about how this local magnetic field affects zero field quantum critical points and why it has to be considered when you talk about quantum criticality induced by magnetic field. So as I mentioned, the entropy accumulation around critical points is well known. This is something that I'm going to show about my project a little bit later. But here we have, as I mentioned, temperature versus tuning parameter, electric field, magnetic field, or pressure. The granizing ratio can be extended in terms of any tuning parameter. And then we have here coexistence phase between coexistence region between paraelectric and ferroelectric or paramagnetic and ferromagnetic, insulating and metal. And in this work, we have proposed that the intrinsic entropy accumulation close to critical points, it can be used to optimize cooling techniques based on the adiabatic conditions. So if you want to do like a magnetic cooling, for example, you should go close to the critical point, so you can benefit from the entropy accumulation in that region. So we have the prediction of maximization of caloric effects close to any critical endpoint. We have also been tackling some other kinds of phase transition-like effects. We have been recently published work about the accelerated expansion of the universe. We have identified that there is omega, the so-called equation of state parameter in the frame of a perfect fluid. That in fact, we have identified this as the granizing parameter itself. So it's just, we discuss in this work that it's not just a numerical constant, but it also has more embedded into, because by making the identification of omega as the effective granizing parameter, we can infer other thermodynamic quantities on the universe, like the specific heat, associate compressibility of the universe, and so on. And then we have used this idea to show that since the expansion of the universe is adiabatically, it's cooling as it expands. It's kind of an barocaloric effect, and we have a signature of this effective Bruneiser parameter when you go from the matter dominated to the dark energy dominated area. When you have like a transition for an accelerated expansion of the universe, and this can be seen as a phase transition like effect, which is something I find very interesting. We have always used these concepts of phase transition and critical phenomena for the so-called liquid-liquid phase separation inside cells. So we can see here that there is something called inside cells. It's like protein compartmentalization. So proteins are synthesized inside cells, and when they reach a particular concentration, it's energetically uh, favorable for the proteins to be inside droplets. So this has a lot of advantage to the cell itself because it reduces noise. And the reduction of noise is really important to uh, minimize defects on the replication of proteins, RNA, and so stuff like that.
What
So
type of
we have
noise
made an
are you
analogy.
talking about here?
Sorry?
What type of noise is mitigated by the proteins being dissolved in a fluid?
Uh, we was talking about stochastic noise.
Okay.
Because the idea is that when a protein is synthesized, it has like a diffusion or a Brownian motion inside the cell. And then if there is a lot of noise because there are a lot of process going on in the inside the cell, the we can compromise the synthesization of new proteins and RNA. So the liquid-liquid phase separation inside these droplets is very crucial to minimize this noise and to control the intracellular process, so to speak. So there are some models that discuss that we can use that actually this liquid-liquid phase separation is just a phase separation, just like a coexistence region I show you in earlier slides. We have like a coexistence region that it's also governed by a critical point. So this is very interesting because then you have like what is said inside the cell, what is like a solvent. It's everything inside. Of course, this is like a simplification of the problem. The cellular processes are much more complex than this. And then you have like bubbles where proteins are inside, analogously to the metallic puddles in an insulating matrix in the metal to Mott Hubbard insulator I showed you before. So the idea is that we have a randomly distribution of these droplets inside the cell, and then we have an intrinsic slow dynamics in particular regions of this phase diagram that enables us to propose what we call a cellular Griffiths-like phase. So we have a Griffiths-like phase in magnetism, where it's like ferromagnetic regions inside a paramagnetic matrix. But here we have like a solvent rich, solvent poor in terms of this liquid phase separation or these protein droplets here. So this is like just a cartoon. So we have like a single phase region where you don't have separation of phases. So you have proteins like being synthesized and diffusion inside your cell. When you go in the vicinity of the binodal line, which is actually this line here, uh, we have the phases start to separate. So you have a slowing down of the dynamics of this diffusion of the cell, which is very beneficial. And then you have what we call cellular Griffiths-like phase because you have two key ingredients, which is random distribution of these protein droplets and the slow dynamics. So this paves the way to define a Griffiths-like phase. And this is important because you have connected this with the origin of primary organism, the treatment of diseases. Is particularly important to disease where liquid-liquid phase separation is present, like even in COVID or in tumorigenesis or some stuff like that. So we have been tackling problems like this in biology too. So coming back to quantum phase transitions, which is one of the focus of my project during Wolfram Summer School, The simplest model to describe a quantum phase transition is the one-dimensional Ising model on the transverse magnetic field. So the idea is that you have like a chain of spins. They only interact with their immediate neighbors. And at 0 Kelvin, they're all lined up in a ferromagnetic configuration. So the Hamiltonian of the Ising model consider two terms. The first one is the interaction term. So we have like J is the interaction exchange coupling constant between the neighboring magnetic moments, between magnetic moments in the site I and the site I plus 1. So this is site I, for example, and this is site I plus 1. So this spin does not interact with this guy, only with this first neighbor. The second term is a term that includes a transverse magnetic field. So magnetic field couples to the spins in the x direction. So if we assume that this is z direction, so the magnetic field is in this direction, so in a transverse direction. And it was actually shown that this, when you apply transverse magnetic field, and when the transverse magnetic field equals the interactions between the neighboring moments, you have a quantum phase transition from a ferromagnet to a quantum paramagnet. I'm going to show you in the next slide a little cartoon of that. But what is in particular important is that when the magnetic energy equals to this, or it's very close in the limit where the magnetic energy tends to the J, this magnetic granizing parameter has a divergence. So it has like a signature that a quantum phase transition is going on. So just to make to give you a little glimpse, we have here a cartoon. Of course, in the Ising model, you only consider up and down spins. So that's why I say this is a cartoon. So I'm allowing my spins to rotate in any angle. Besides up and down. So if you have like 5 Kelvin, for example, they're all in random configurations. And as you decrease temperature, they all start jiggling around, and when you achieve 0 Kelvin, they all line up in the ferromagnetic configuration. So this is exactly the same picture I showed you before, but now I have brought my system from a finite temperature to a 0 K. And when we increase the transverse magnetic field, like from left to right, for example, when I have magnetic field close to 1, when this the energy of the transverse, the magnetic energy is comparable to J, to the exchange interaction, the spin starts to flip in the direction of the field, and this is what I call, or the community of the literature calls, a quantum paramagnet. This is a quantum paramagnet because if I remove the field, it goes back to the ferromagnetic configurations. But this is the simplest example of a quantum phase transition. So this is something I find very interesting to explore. So in terms of this, we have been working on the quantum version of the one-dimensional Ising model to show that if you remember correctly, the Grunizing ratio, it has thermal expansion divided by the specific heat. But what happens if we put like 0 Kelvin? If you put like 0 Kelvin, all quantities, according to the third law of thermodynamics, entropy should be 0 at 0 Kelvin. So all quantities that relates to the entropy must be 0 as well. And that's the case for thermal expansion and specific heat. So you have like the Grunizing ratio that is not valid anymore for 0 Kelvin. So what we did was to propose a new Grunizing parameter that is actually valid in 0 Kelvin, where now we have, instead of the free energy, we have the ground state energy. And instead of the thermodynamic entropy, we now have the von Neumann entropy, or the quantum entropy. And the idea is that we have used this for the quantum version of the one-dimensional Ising model. And we have shown that this Grunizing parameter has a fingerprint of the quantum phase transition. I just showed you in the cartoon before, exactly the same way that the thermodynamic one. And the idea behind this work is that we have proposed that optimized quantum computing is quantum computing is optimized in the vicinity of quantum critical points because you have an expressive variation of the von Neumann entropy when you vary, for example, in this case, the magnetic field. And this is very beneficial to quantum computing in terms of resilience of your system or in terms of computation.
So,
And that the phase compute.
I have a question.
Yes.
What's the advantage of having the temperature low? Is it that the spin states can be more easily aligned when the temperature is low?
Actually, in this particular slide, I'm considering we are at 0 Kelvin. So they're all lined up in a ferromagnetic configuration. But the idea, if I go back to this, uh, if we think about entropy here, the entropy here is not zero because you have different configurations between the spins. So as I decrease temperature, the entropy goes to zero. So this is a zero entropy configuration because you have only one state available in your system. So this makes the entropy to be zero. But I mean, this is now talking about this is a theoretical work, assuming that we can access experimentally 0 Kelvin. So there's no temperature involved here. Uh, Now the ground state of my system is already a ferromagnet. So now I'm going to apply the magnetic field in the transverse direction to induce the quantum phase transition. So what we are saying is that in systems used in quantum computing that present a quantum critical point, for example, you should go there in the vicinity of the quantum critical point if you want to optimize your quantum calculations in terms of quantum computing. That's what we're talking about here.
Okay. And
Okay?
what is lambda in this diagram?
Lambda is defined as the ratio between J, which is the exchange coupling, and the magnetic field. So lambda equals to 1 means that the magnetic energy is comparable to the exchange interaction between spins, and then they flip in the direction of the field. So you have to, so to say, overcome this interaction when you apply magnetic field. So they go from this configuration to this. Since in the definition here it's a J over B, so from right to left we are applying magnetic field. Okay.
Thank you.
And last but not least, what we shown in this work was there is a breakdown of the Hellman-Feynman theorem at any quantum critical point in the thermodynamic limit. So there are some peculiarities over that, but we have shown that not only our new Grunizing parameter is has a fingerprint in terms of the quantum phase transition or the quantum critical point analogous to the thermodynamic one, but we were able to infer that quantum computing is more expressive in the region close to the quantum critical point, and also that at this particular point, the Hellman-Feynman theorem breaks down because you have a huge increase in the variation of entropy if the tuning parameter of this case is the magnetic field. Okay, and as a natural continuation of this work, um, I didn't mention in the previous slide, but there's a divergence of the Grunizing parameter here that we continue to explore in the next work. So the idea is that we have published this work together with Professor Constantino Salles here from Brazil, from CBPF. And we discuss about the divergent quantities in, so to speak, in critical points. So the Grunizing ratio or other thermodynamic ratios only diverge on the critical point because right at the critical point, the entropy, the Boltzmann-Gibbs entropy loses its extensive properties. So what we did in this work is to apply the so-called Salles entropy and to show that for a particular value of Q, this is the so-called entropic index, uh, this particular value of this entropic index that recovers the extensivity of the entropy right at the critical point, there's no divergence anymore um, of any physical quantities like the Grunizing parameter and so on. So we have like corrected or make a um, we brought back extensivity of the entropy right at critical points, by making the entropy extensive again by using Thales entropy and its corresponding entropic index. So you have like this is the main result of the paper. For values of Q lower than this the so-called special value, you have that the inverse of the agonizing ratio diverges, and that for higher values of Q it goes to zero. But right at the exactly value that brings back extensivity of the entropy, there's no divergence anymore. So this divergence associated with critical points is suppressed when you regularize, so to say, the theory of critical phenomena by bringing back the extensivity of the entropy right at the critical point. As I mentioned, this work was done with Professor Constantino Tsalis, the same one that are in Mathematica we have like two built-in functions. We have the Tsalis Q Gaussian distribution and Tsalis Q exponential distribution. Just curiosity associated with this. So, and then comes Wolfram Summer School. So Wolfram Summer School was really special to me because it could like merge this background that I had in critical phenomena and phase transitions in a project that was suggested by Stephen Wolfram in terms of cellular automata. So the idea of my project starts now. So the idea regarding cellular automata is that we have some so-called mechanisms of consensus based. So we have like different nodes, red and yellow nodes, that the idea is that the algorithm updates the color of the nodes depending on how many nodes of that particular color around it it has. So in this case, we have like a five neighbors algorithm that every time it iterates, it changes the color, and you can see that eventually you go from a mixing between red and yellow, and you go to a full yellow node. So this is what it's defined by consensus. So if you achieve like a full color or a full, so to say, color of the node, and then you achieve consensus. So that's the main idea. So if you have like rule 232, if you start like with 60% of so of course this is like a 1D cellular automata. And if you start like if 60% of red cells, and then you can see that after a while, you achieve a full line that it's only red. And the same happens if you start with 40% of red cells, that is 60% of yellow cells. Eventually, after a number of steps, you achieve like a full yellow line, saying that, meaning that you achieve consensus. So, what in this project, what was done was to show that if you can compute the average density over steps for different kinds of initial density of the red squares, you can see that for values higher than half, it converges, it achieves consensus to 1, that is, they're full red, or for values of initial density lower than half, you achieve consensus to 0, which is corresponds to a full yellow line. But right after 50%, so if you start exactly 50% yellow, 50% red, you don't get consensus at all. So it's just like this straight line. So the idea is that you don't have a convergence of the average density, and this is something that is similar to a critical point, because right at the critical point, the system cannot decide which phase it is. If it's like a liquid or a gas phase, if it's like a ferromagnetic or a quantum paramagnet. So there's like no consensus right at the critical point. And this, using the so-called 7 neighborhoods and GKL rules, what was done was to insert random noise on each step of this cellular automata. And the idea is that you can have like a phase diagram of noise level versus initial density, where the color here is the average density. And you have like a very close situation to a quantum phase transition or a quantum critical point. So you have here on the left consensus, here you have consensus 2. but now in red. Here you have local consensus where you have like you don't have like a 100% line of full red or full yellow, but you have like I don't know, 97, 95% of red or yellow. So this is what called local consensus, and this is what called global consensus. And if you start increasing this so-called noise level, you achieve no consensus. So this looks like very similar to these phase diagrams I showed you before, where the critical point is right at zero point 0.5 initial density. So how's this random noise is added? So the idea is that we start with a particular configuration of cells, and then you apply the rule. And then after you apply the rule, we're gonna randomly flip some of the squares depending on the noise level and the length of my chain. So that's why I put here that the number of flipped squares equals the noise strength or the noise level times the length of my cellular automata. So for
Okay,
example, if
so
I have like, yes,
um, right. So this is a one-dimensional cellular automata, right? And can you describe the rule that's
yes,
being used? Is it just you have a neighborhood, and then you want
yes,
to like take the see which one has greater density, or which one wins in that neighborhood, and then update the cells
exactly.
using that majority vote.
Sure.
And then
So
so what are the sizes of these neighborhoods that you're
so it's seven neighborhoods. So
working?
we look for the three on the right, three on the left,
Uh-huh.
and the majority color that wins makes the cell to flip or to keep it as it is.
Hmm. Okay.
So if you have like a red square, and then you have, for example, I don't know, three yellow on the right and two yellow and one red. So the yellow wins and it's gonna flip from yellow to red.
Yeah.
Red to yellow, sorry.
Right, right. So it's an odd number of the size of the neighborhood. All right. So you have like the cell and that's three neighbors to the left, three neighbors to the right. That's seven cells, and so with you're gonna have a majority vote no matter what with
Yes.
that odd number of cells, and then do that. Okay. So um, and then tell us about this flipping, this stochastic process in the middle. So you update the rule, you do the rule update, and then
Yes.
you add noise into that.
Yes. It's a random noise.
Okay.
So the idea is that these GKL like rules, they're well known for their uh, robustness against random noise. So that's why this was thus chosen. But the idea is that we have three on, for example, as you mentioned, we have three squares on the right, three squares on the left, and then we apply the rule. So this square of a particular color, red or yellow, is going to be updated or not, depending on which color wins. After you apply the rule, I my program randomly flips uh, some of the squares depending on the noise level I'm inserting. So, for example, if I have like a length of 100 my cellular automata and my noise level is 0.05, after step I'm going to flip five squares out of 100, for example. And then we can see the idea is that to check how so we can see here that depending on the noise level, this noise level can destroy or can suppress consensus in such a way that you don't get like a full line of yellow or red. And this is particularly important for a consensus-based mechanism like blockchain technologies, for example, that relies on a consensus to validate a certain transaction or a certain block, for example. Okay, so then this is the consensus-based mechanism. Now I'm going to start with some results. So what I did was to start, for example, with 40% of the initial red cells, and then I compared what was the average density over steps with and without noise. So we can see that without noise, uh, as I showed in the examples before, in Rule 232, eventually some steps it will go to zero because it will converge to a full yellow light. But if you put noise, this will oscillate a little bit, but eventually it will converge not exactly to zero. I mean, not exactly to 100 full yellow, but to a value close enough, like 95% of yellow. And this is the difference between global and local consensus. So the idea is that depending on your, so to say, problem, depends on your threshold of consensus you need. For example, in blockchain technology, sometimes you have like only to have a 51% of consensus to validate a block. So here we're talking, we can modify the noise threshold or the consensus threshold. I'm going to show this in a little bit later slide to show to reach my desired level of consensus. So for example, here we have like the very same noise level versus initial density. And this is the lines that separates consensus to no consensus depending on my threshold. So the blue lines here indicates the convergence to a density of lower than zero point 0.1 or 0.9. That is, it's going to 90% of yellow squares or 90% of red squares. So this might be important to uh, because sometimes, as I mentioned, you don't have to have like full consensus. And then you can tighten up that threshold, for instance, to 95, 97%. And then you have like part of the project was to construct this algorithm to determine these lines which separates the, so to say, the phases, like the yellow and red phases that are very similar to the phase diagram of quantum critical point that I showed you before.
So when there's no consensus,
Sure.
uh, what does that dynamic process look like? I mean, what
When I
is
have
the
consensus,
when you don't have consensus? Is it like you have competing like red and yellow regions in the cellular automata, like sloshing back and forth, for instance? Or...
yes, I mean you achieve like I didn't put an example here, but you achieve like a configuration of not on 100% on a full color, and then this perpetuates no matter how long you take the system, let the system evolve, you never reach full consensus. You only reach like a local or partial consensus. So. Um, and this is particularly strange, so to say, right at a half initial density, because you have like this beautiful patterns that appear but prevents the a full line of a single color. So that's what usually happens.
Got it.
Okay. What we also did was to check uh, how much what's the effect of skipping random noise in the initial steps of the computation. So the idea is that if I put noise at every step, the average density will oscillate a little bit, but eventually it will converge, as I mentioned, to a value not exactly zero, but close enough, which means that the system went to partial consensus with the majority of squares in yellow, for example. But if I skip noise in the five first steps, I can see that the consensus is reached way faster. So this makes sense because an important message here is that the initial steps are very much sensitive to random noise. And then you can reach consensus faster or slower depending on how much and how early you insert noise in your system. But
Question.
this is very,
Yeah, so
yes,
this is delaying the introduction of the noise.
yes. So in the first five steps, for instance, in this blue curve,
Mhm.
I only apply the rule. I don't randomly flip the squares. So after the five steps, I start applying the rule and then randomly flipping the squares. So that's the idea. Just to check how sensitive the cellular automata is to the first, to initial conditions, so to say.
Uh-huh.
Okay?
and the red is noise that's being applied at every step, starting
Exactly.
right away.
Exactly. So I start with the first line. So this is the for start with 40%. I mean 60% of yellow, 40% of red. So we start here, but we start like we apply the rule. In the next step, we randomly flip, and then it goes on instead of just skipping the first five steps and then start adding the random noise. So we can see that there's a dramatic the consensus is reached way faster when you skip only the first five steps.
Right, right.
Okay?
And it took like 1,000 steps for it to get down to that lower level
Exactly.
for the
Yes.
one that started out with noise, but for the one that had like a just a five step like head start, so to speak, it
Yes.
went down to consensus or to that low noise
Yes.
level, the density level, very quick.
Yeah.
Huh.
But this result seems interesting, but there is something that I bounced, so to say. I bumped it. Um, that I think it's a little bit more interesting because usually when you reach consensus, it's done. You reach consensus, your system stays in that configuration like forever. But I thought I saw some patterns like this little spikes, and then I thought that is that a pattern here? Maybe I can extract something like that is like periodic or you have a frequency. But for my surprise, when I increased the number of steps, what I observed that because for the system with noise at every step, uh, for a particular number of step, the consensus flipped from 0 to 1 because of these critical fluctuations. So the fact that I keep adding noise and every step makes that for some particular point this flips. So this was a surprise to me. So it's like this is like quite abrupt, so to say. So this is like an analogous situation to nucleation. Nucleation, like when you have, um, for example, when you heat water in the morning to make your coffee, and then you see that although there's air or there's air embedded in your water, you cannot see the air. But as you heat up, the bubbles emerge. So this is what I mean by nucleation. So these bubbles depend on a critical fluctuation to appear. And this seems like it's the case. So it's very interesting that I thought that consensus was going to be reached and that's it. But it seems that this consensus um, depends on how wide of how big the number of steps you are investigating. So this is something that we are going to probably explore further in the future. And
Yeah,
this is
it's a
something
very
that I find.
curious result. I'm curious if this experiment was carried out many times, would you get the same sort of 25,000 step count like that? If that threshold is sort of at the same place and time, or if that changes, and if it does change, what's the variability? And why does this happen?
Exactly.
Is there something like accumulating hidden behind the surface, and then all of a sudden, like you've reached the threshold?
Exactly. I mean, determine this particular threshold for this to happen. It's definitely included in future projects because here I have a 100 length cellular automata. So if I increase a little bit this, I'm gonna say that this effect disappeared, but I'm not sure if this disappeared, but only was shifted to higher steps. So that there's many variables here. We can change the length of the chain. We can change the initial density. We can change the noise level. I mean, we can explore this further, but it's definitely a very interesting result that was a surprise to me.
Yeah. We have a question from the audience. Ellie
Sure,
asks, have you thought about how the noise might be distributed in less random ways? For example, large areas of similar valued cells
sure,
may be less vulnerable to noise disruption than
sure.
smaller areas.
That's the outlook of this presentation. So this is everything I'm discussing here is regarding random noise. So we're definitely going to explore different kinds of noise that add into the system. So thank you very much, Ali. Okay.
Yeah, another question. I guess are these CAs on an open system, or are they confined to a cylinder? Are there periodic boundary conditions on the CA?
Periodic boundary conditions, yes.
Okay. Yeah. So I guess one thing to kind of look into is sort of, yeah, if you had instead of just a uniform distribution on that doing the random flips, adding noise, I guess, see if concentrating that noise into tighter regions would, like you say, nucleate um, a pattern which kind of takes over.
Yeah, probably.
Mm,
And
mm.
we're definitely looking forward to see those results pretty soon.
Exciting.
Okay, great.
Mhm.
So the next step is to, as I mentioned to you, there's an entropy accumulation around the critical point, and here we have made use of the Shannon entropy or information entropy to compute the entropy for a particular value of noise level in terms of initial, sorry, in terms of density. So we have here, it's like I'm going to show in the next slide, but it's like a slice on that phase diagram. So imagine if I'm horizontally scanning that phase diagram. So we have that the average entropy as a function of density. It has a peak right at half density. So this is an analogous situation. So I showed you before that entropy is maximized or accumulated right on critical points. So as we increase the noise, so this is for zero noise, this is like 0.01, 0, 0.02, 0.03, zero point 0.1, and 0.15, you can see that not only the entropy is broadening, but also the entropy variation is being suppressed. So here you can see that we go from zero or kind of zero to 0.25, but here for high noise, it's varying in the it's a very low variation. So that's why we are going away from the so-called critical point here. Um, and this is pretty interesting because it's an analogous situation to a critical point that we can map. So you can see this is the phase diagram I showed you before, and this is the entropy lines. So this is where the critical point is. So you can see that as I increase noise, this variation of entropy is going to be suppressed so that in this region where you don't have like consensus anymore, the entropy is just like a flat line. So we can see that the higher the noise, the higher you increase the value of the entropy, but you don't have like this fingerprint of entropy accumulation anymore because you're away from that particular special point. And so what we can do is like to make like a counter plot or a density plot in terms of noise level and initial density. And you can see that this is the special point here right at half, but there's like the entropy is very low on these regions here because you have consensus. That means you have like a single phase or a majority of one phase analogous to the ferromagnetic phase I show you that has like zero entropy. And then as you tune your system into this point, entropy is going to be accumulated here. And then you can see that it spreads uh, in this region of noise level here, and then here the entropy, you lose this maximum here that I showed you before. So we were able to make an entropic mapping of the phase diagram here that was pretty cool. Also, as the last result I'm going to show is that we have explored the size effects. So what we did was to make compute the average entropy in terms of initial density, but for different sizes of cellular automata. So what we could see is that the higher the length of the cellular automata, the higher the peak of the entropy right at the density equal half. So this is something very interesting too. So as conclusions for this presentation, a high noise magnitude dismantle consensus. That's the main idea. And that's what we explored, how much noise level we can put in the system so that it's resilient against to achieve consensus or not. So the determination of the consensus depend on the noise threshold or the consensus threshold. If I want to achieve like a 95, 90% of consensus, or no, I need to 100% consensus. That's depend on your problem. And the entropy is maximized right at uh, the density equal half. So there's an absence of consensus. An analogy to the critical point in physics where the system doesn't know if it's liquid or a gas or a solid, so there's no consensus on that. So for outlooks, we're going to explore the same thing with random noise, but in 2D cellular automata. And also we have to, as I mentioned before, regarding to Alice's question, we're going to modify how noise is added into the system. Like we're going to play around with different noises and see how it changes consensus or not. So I would like to acknowledge first Stephen Wolfram for proposing this project for the Wolfram Summer School and for this amazing opportunity. My mentor Rafael Caballero, my postdoc supervisor Professor Mariano de Souza for proposing some of the topics, some of the calculations here. Stephanie Bauer for her amazing support for me attending the Wolfram Summer School, and Daniel Carvalho, Bowen Ping, and Tarang Jenna Walker for code-related support and other stuff. Before I finish my presentation, I'd like to share with you that we have a YouTube video channel. Uh, it's called Physics Knowledge, translating to English. So we recently posted an interview with Stephen Wolfram that I had the honor to do. And then if you are more interested about that, the idea is to broadcast science for a Brazilian audience. But if you're more interested in that, please take a look at the channel, subscribe, like, and you're more than welcome. And so, thank you very much.
Thank you so much, Lucas. Do we have any questions for Lucas? James, Nick? Well, I have a question. So
Sure.
with this consensus protocol, is there ever like an instance where like there are just more like yellows than reds, but like the reds win out in the end?
Well, I think that this is like let me just go back to my presentation. I think this is like a situation that you're describing because usually the majority of the color, like if there's a majority of the colors of yellow, for example, after a number of steps, it's natural to expect that the yellow is going to win. So in my view, I would never expect that the red is going to flip. So I think that your question is regarding it's perfectly matching this kind of behavior is seen because the idea is that not who's winning, but who's winning and at that particular time of at that particular step, because it can change, it can flip depending on if you increase the number of steps or not. So I think that that's the answer. Um, it's like we have like a so to say butterfly effect. If you add random noise to a particular position of the squares, it will perpetuate in a way that it will make eventually the red cells to so to say percolate. So that's why I put here that's like a critical fluctuation because it's like a correct fluctuation in the correct position of your cellular automata that is eventually leads to a flipping of the consensus. So that's I think that the analogy to butterfly effect is like it's nice.
So yeah, when you
Right, but that rule, sorry, one sec. That rule, like if you have 49% red cells on the first row, for example, the initial condition, it will never go to red. It will always go to yellow
Well,
if you don't
yeah.
add any noise.
Oh, if I don't add any noise, yes. So if I don't add any noise, so if I have like 49, it will go to yellow. If you go to 51, it will go to red. If you go to half, it stays like
Right.
undecided, so to say.
Okay.
So no, noise is responsible for doing that. I think that's what you're asking, right?
Right.
So Dugan, I think you had a question.
I was curious about the density of the noise that you're adding in. Was that always
The
held constant?
The noise level, yes. So the idea is that, as I mentioned, the noise level and the length of course, I fixed the length of the cellular automata and the noise. For example, here I have um, uh, cellular automata of length 100 and the noise is 0.05. So every step, 5 squares are being randomly flipped. So uh, I kept that fixed for this particular result, but we are looking as next steps to, of course, play around with this and to vary the length, to vary the number of the noise level, and see if this effect, this particular one, it holds, and in what particular condition it still holds.
Yeah, this definitely needs looking into. Very curious about these results.
Yeah, weird too.
I have a question about the Griffith phase inside the cell piece.
Sure.
So, what does Griffith phase like look like, or yeah, what does it look like, and how is it
Sure.
similar to the cell? I didn't quite get it.
In magnetism, a Griffith's phase, I mean, Griffith's phase was first defined in the context of magnetism. So Griffith's phase, for you to have a Griffith's phase, you have to have two ingredients. The first one, you have to have like the so-called rare regions. That's in the magnetism is the ferromagnetic islands inside a paramagnetic, so a magnetized region inside a non-magnetized region. And so we have to have a random a distribution of these puddles or these bubbles of magnetized regions. And then you have to have slow dynamics. What means low dynamics? Is like you can talk about autocorrelation function, you can talk about the dynamics of your system, but when you have these two ingredients, slow dynamics and random distribution of these rare regions, you have what is defined in physics as the Griffiths phase. And for it was very interesting that we find a similar scenario of this in the case of liquid-liquid phase separation. So this is analogous to the magnetized regions here in a non-magnetized matrix. And then we were able to extract the dynamics of this to show that when I cross, for example, the boundaries of the single phase to the two-phase region, the the dynamics of the system are becomes low. So when you cross this in the vicinity of this line and for the concentration of half, which is essentially very similar to the problem in the consensus-based mechanism, then you have these two ingredients that enables us to propose the cellular Griffiths-like phase that has, as I said, implications in many scenarios like the primary of or the origin of primary organisms, the medicine, the treatment of diseases, and so on. So that's a very like scenario of magnetism. So that's where Griffiths like phases are.
Okay, so basically, as you're saying, this inside the cell is like this two phases region, right?
Yes.
Or no? And it's just everything is kind of moving slower, so it's almost like molasses.
Yes, but depends on where you are in the phase diagram. As I mentioned, these slow dynamics occur only on the vicinity of this line. So
Okay.
if you are like here, that it's not in the half to half, like half protein, half solvent, or you're not in the vicinity of the bind on the line, the dynamics is not necessarily slow. And I
I
forgot to
see.
mention, but this work here, we applied a very similar mechanism to propose an electronic Griffiths-like phase. So here, instead of in the Griffiths phase, I mentioned it's like a magnetized regions inside the non-magnetized matrix. So here we have like a metallic puddles inside an insulating matrix, and here we have like a protein condensate inside the protein pore solvents. So we'd like to explore Griffith's phase, and this is like two examples of ongoing work that we have able to recognize Griffith's phase in the electronic and the cellular phases.
Interesting. Thanks.
Oh, thank you for the questions.
Yeah, yeah, really interesting. A lot of different applications of we're looking at phase transition, like in biology here,
Yeah,
and then in material science and icing model for quantum physics, and yeah,
exactly.
always helpful to look at minimal models for phase transitions and for cellular automata.
Yeah.
All right. Um, I think we can, unless we have any more questions, I think we can close down the live stream. So, yeah, okay. So I want to thank you again, Lucas, for coming on and presenting your project. Very interesting work.
No, it's my pleasure. I thank you, Max and James, for the invitation and for me to be here. Thank you very much.
Mhm. And just some
Great,
announcements.
thank you.
Um, tomorrow at the same time at 2 p.m. Eastern, we have a presentation from Flo Foxconn about using AI transformer models to predict graph rewriting. And then on Friday, we have another live stream presented by Peter Shen, his project on symbolic regression with Kolmogorov-Arnold networks. So thank you all for tuning in, and we will see you again next time.